Hi, my name is Matt Graham, and for the past month, I've been working on emulating an effects signal chain using an evolutionary algorithm. Current audio industry is obsessed with the vintage sounds and hardware of the 1960s and 70s. However, it lags behind in adopting new technology like artificial intelligence. From the AI side of the house, not a whole lot of research has been done into applying AI to general audio processing as opposed to something more popular like speech processing and recognition. Now what I would like to do is to plug my guitar into an expensive effects pedal. However, I don't have that kind of cash. So what I attempted to do instead was to plug my bass guitar directly into some AI magic to see if I could get the same output. For a general overview of the project, I applied a basic evolutionary algorithm to the problem. Give the algorithm an input signal, a target signal, and it will attempt to evolve a network capable of transforming the input into the target. However, this poses a problem because audio frequency data isn't very neural network friendly. Thankfully, we can use Fourier analysis and the Fourier transform to get data more suitable for consumption by neural networks. Now, if you're not familiar with the Fourier analysis, it's pretty simple. Feed in a signal, like on the left, and it spits out an array of values that are intensities of frequencies present in that signal, like on the right. But the basic Fourier analysis isn't powerful enough to get all the information I need out of the signal. This is where the short-time Fourier transform comes in. It applies a basic Fourier transform over small windows over the entire signal. The STFT is suited for the job because it still retains some information about the time domain that is lost during the regular transform. After applying the STFT, the result is then binned into some number of frequency intervals. One of the most important aspects of the STFT is that it's invertible, meaning the original audio signal can be reconstructed from the STFT data. One problem with the Fourier analysis is that the results include complex numbers. To deal with this, I had to apply one more transformation to the input data that I will refer to as the coefficient transformation. Essentially, it breaks the array result of the STFT up into its coefficients. This way, the result can be modified without giving special treatment to the imaginary part of the complex numbers. Once the input is ready to go, it gets put into a network that looks a whole lot like the one that's on screen right now. An input layer is sieved into a set of smaller, fully connected layers which are then piped back into a fully sized output layer. Finally, the inputs are connected directly into the outputs. This gives many of the benefits of a fully connected network without as much complexity or as much compute time. So the full pipeline goes like this. The input and target audio files have the STFT and coefficient transformations applied to them, and the results are written to files. This is the pre-processing stage, and it can be done entirely ahead of time. These files are then read into the algorithm, where evolution is applied using the standard evolutionary algorithm. The result of this is a file containing modified STFT data. This data has the inverse coefficient transformation applied, and then the ISTFT applied to it, resulting in an audio file. Then we cheat a little bit and apply filtering to remove some unwanted noise. Before we get into the results, here are a few chromograms of the input and target files. Chromograms show intensity of frequencies binned into classes by musical notes. Brighter color means more of that class of frequency at that time. If you're watching this on a projector, the colors may be difficult to see. The results are a little bit mediocre, but substantially better than I thought they would be. Again, if you're watching this on a projector, the colors are going to be hard to see. They show promise, though. The extra harmonics added to the target signals by the effects chain can clearly be seen across the entire board of results. Fitness was calculated as the negative mean squared error between the signal produced by the network and the target signal. The mean squared error between the original input signal and the target signal is approximately 20, so the best networks have made quite an impact on the signal. Now for the audio results. First, the input signal. And now the target signal. And now the unfiltered output signal. And finally, the filtered output signal. Future work includes finding a different way to transform the input that more closely corresponds with the audio itself. The STFT is very powerful, but the coefficient transform is more of a hack than anything else. It would also be interesting to experiment with a different evolutionary algorithm or to even apply deep learning to the problem. Thank you for watching.